Is everything clear in regards to the implementation of the task, which is not that complicated as we've seen, because basically the encode is just a while loop. Oh no, I get partial points. Okay, this is because the binomial coefficients that have initialized go up to 1 million, but as we've seen, we can have a sum of the coordinates, which having both of them up to 1 million would mean that we may have the binomial coefficient up to 2 million. Okay, now I get time limit exceeded, which is hilarious. Normally I'd overlook this because it might be some funny thing happening with these values. I left and right diagonals in O of n, but it's not O of 2n because this is, I mean, you might be right because as I've pointed out, normally, where was I? Because the binomial coefficients that we subtract are also in a line. So then they also correspond to a hockey stick-like identity. But it's, normally I'd overlook this and I really won't overlook it because we have 96 points. So it's just a matter of and I'm not sure how relevant it is to, for the sake of the bit of programming, to have to erase one more trivial calculation, although it might halve on the time, but it's just a calculation. I think that it's 70 seconds. If someone wants me to really have it on the stuff I have, it's easier. Okay, then I will move on. I hope the implementation, at least for the binomial coefficients, which was the really important thing, was clear. Okay, I'd like now to talk about problem A, which says a lot of things, but they're mostly irrelevant. They say that we consider an array A, we construct an array B formed by the sum of all the subsets in A, including the empty one, but that's very irrelevant. And we continue applying this same operation where we keep taking the set of all the subset sums repeatedly, basically. And we have to print the sum that we have by the end. Normally, if A equals 1, I think most know this. we solve it. Oh, now I'm the third person to solve it. So if we have an array A and we consider the subsets of A set at the S, then any X in A would appear due to the size of A minus 1 times in some subset of S. Does everyone agree with that? I hope you do. This is obviously because we can just create any subset without X and then add X to it. And add these many subsets. And then obviously X would contribute to the sum of S with X times that value. But what happens when we take the subset sum of all the subset sums is that now we have 2 to the A elements, and X belongs to the A minus 1 of them. And we take the set of all the subsets. What happens? Wait, I'm a bit confused actually. Normally I expected this to be just 2 to the yeah, something okay, obviously X will not belong to a subset that is not in one of these subsets. But then there is a coefficient. Oh yeah, so then it doesn't matter. Okay. Consider one of the sums where X appears, then that single sum, one of these 2 to the A to the minus 1, would then appear in 2 to the A minus 1, 2 to that much. Because we can take any subset of all the other subsets and ignore X from that one. And then we have to multiply this by 2 to the A minus 1. Oh no. Okay. So have all the subsets. We take any subset where X belongs to, where X appears, X contributes. Then we take any subset without that one subset, and then we choose which subset we chose X to belong to initially. And this formula cascades further that if we have a set of elements and some value X belongs to set of elements belongs to K of them, then we have to compute and we have I operations left. Then we'd have to see in how many times any one set one element on T would appear after applying the operation on T more times, and then multiply this value by K. Thing is that I'd expect to have by the end is some sort of power tower that looks like this. And some minus ones along the way. There's somewhere here minus one. We'll see about that later. But that's how we would implement this, I guess. So normally we know that 2 to the power of mod of the distortion function of the mod is equal to 1. But then we know that inside the exponent we have another binary exponentiation. That is 2 to the, let's say, k equals 1. And really what we want is now to calculate to the power of k modulo pi of the initial modulo. And if k is a power tower of its own, then we have to calculate this modulo phi of mod. And as I've proven and shown in one of the documents, this value phi of mod, which is the count of all coprime numbers less than mod, this is almost logarithmically upon applying it multiple times. That is, strictly speaking, how it become that 2 to the phi of mod equals 1. So that is a little bit of group theory. But technically speaking, if we were to consider that mod, the modulo that we use, is not really coprime or anything like that, although it might end up this management will resolve that. It's not really prime. Then, if you are to consider the set of all numbers such that they are coprime with this mod, these elements form a group. That is, we can multiply them one with another, take the residue modulo of this value mod, and then we have another element within S. Well, that just means it's closed, but obviously associativity, invertibility, and existence of an identity element that is simply just one follow trivially. In such a case, we know that mod does not always need to be prime. So long as we do operations with those elements that are co-prime to it, that is, they do not share prime factor with it, then we are in the clear. And because this element, this set with multiplication forms a group, we can conclude that normally the order of any element divides the size of the group. That is, the index, the smallest value such that x exponentially x to that power is is equal to the identity element divides the size of the group, which means that we can just raise this again to the power of what is left. And get at x to the size of the group equals 1. And by definition, phi of mod is the size of this set. It's the count of lesser elements that are co-prime with mod. So as long as 2 and mod are co-prime, this identity holds. Which makes me a bit nervous because now I realize that phi of mod will obviously be even at some point in time. And I really didn't think of this that much initially. In case, let's try to calculate this value, which is do. Iterate over all the letters. And then if we find such a prime divisor, we erase it completely from our number, and then the result becomes as I said, in the document, this value basically. That is, normally we'd expect modulo any prime. It's considered p to the e. That obviously in such a case there are p to the e minus p, the e minus 1 co-prime elements with p to the e. Obviously, because this is the count of multiples of e until p to the power of e. And if n is described as a multiplication of more such powers of primes, out of the Chinese remainder theorem, we can choose a residue modulo each of the prime powers. Then we'd get a number modulo n with those residues, all of which are co-prime with every single power of primes that compose n. And so we compose the number that is essentially co-prime with n as a whole. And so we'd have to multiply by these prime powers, which are simply reduced to p to the e times p minus 1 over p. And since we multiply with every single prime power and then this subunitary coefficient, the product of all the prime powers is essentially just n, and that is what happens. Normally, when we calculate this, we have to also take care of the case where n still has a divisor left, although it would be the last one and it wouldn't be at a power higher than 2. And then on this second case, we have the same reason. all of this to say that essentially there is basically like because the order of the elements or whatever does not really matter. We know that every single x in S in the initial A will appear just as many times in the final sum as any other of its colleagues do, so to say. Oh yeah. Okay. The issue, as I've said, the issue is that we'd have to calculate this value, which normally doesn't really make sense. Maybe the case of the problem actually circumvents that entirely. I'm not really sure how it would in the first example. Oh, how I met actually so I just to be however, apparently it isn't. Uh, oh no, oh no, they do something much worse. Oh god, oh no. Okay, uh, log mode. Yeah, uh, and normally have to, at first, I think I have to figure out what the target value is, and only then can I maybe work the way I'd want to. Okay, I apologize, but I think it might be a waste of time if I continue to try to figure out this task. Which I really hoped it would be a simple exercise to showcase this and then this, but it might be the case that this is not really an accurate formula for whatever reason. And later then I'd have to, it seems that what they do is something related to uh, constructing this set of so essentially what might happen is that we'd have to factorize this element, or it might prove that obviously the more we multiply by 2 and we, let's say we calculate 2 to the power of 100 modulo 24, and this will almost be equivalent to 2 times 2 to the power of 99 modulo 12, then 2 times 2 to the power of 98, 2 times 2 times 2 to the power of 98 modulo 6, and 2 times 2 to the power of 97 modulo 3. And after calculating this, which we are allowed to, we don't really do that. Do this so stupidly. Please, PR, whatever. Upon calculating this value, we are free to then multiply by whatever value we have here, because we work modulo number, which is obviously co-prime with 2. Should I continue? I think we could instead, I could instead showcase implementation of this task, which no one saw, so it should be interesting. And then I'll move on to the Q homework. Okay, so normally we expect that if a number has some divisors, D would be equal to basically this. Where E1, E2, and EK, K are the prime, the exponents of each prime number that compose the initial number. So if E were be equal to P1 to the E1 times P2 to the E2, then the count of divisors would look like this. We can obviously take any power of any prime, and we have E1 plus 1 such powers of P1, E2 plus 1 such powers of E2, and so on. To compose T, to compose a divisor of T out of, and then that would mean that there are that many divisors. Their prime factorization contains exactly k distinct prime numbers. So we have to split T into numbers of length k. And all prime factors in their factorization are less than or equal to p. This is a trivial caveat that no one actually can, because then what it means is that we have to select they give us basically to choose the prime powers that are otherwise not described within this equation. Furthermore, expect that for the sake of simplicity, that when we divide D into a product of otherwise such divisors of D itself, that we do so in order of the prime bases that represent each of these exponents. So then by the end, really what we have to do is multiply by count of primes less than P, choose K. This can be very quickly done. I apologize that this could be I, but okay, we'll do this then. So E, E, K, and as I said, the number of primes, choose K. Okay, now on to solve the real problem, which is how, I don't think it's really that much. Or at least I should be missing something. Oh, yeah. Okay, I see. Okay, so the task at hand now asks us in how many ways we can split E into a product of divisors. Basically, we can ignore the fact that the divisors have to be the form of E1 plus 1. But what we cannot ignore is the fact that every E to the EI has to be greater than 0. Because otherwise, there won't be that prime base included in the final number. So then we don't actually have K prime numbers in the factorization, which they really ask us to have, but we'll have less. What would come to mind would be to make maybe some sort of dp of D equals dp of D of K or something like that, equals dp of D over some value C, K minus 1, dot sum of, let's see, divide, and then print dp of D of uppercase D of uppercase K. The problem is that the number of divisors of D might be around, in such a case, let's say 10 to the power of 4. And then fixing another subdivisor of D would also be 10 to the power of 4 times K. It will surely time limit for a suitable selection of D. So instead of calculating of distributing divisors one by one, we can instead distribute prime powers that compose D into each of these blocks. Is that by the end, normally if we do such a parallel distribution, that is, we distribute all the powers of 2 that compose D into all the divisor slots, and all the powers of 3, then all the powers of 5. That is, if D is divisible by 2 to the power of 3, we have to distribute 2 into these groups a total number of 3 times. That is, we can say that this divisor will be divisible by 8, or we force that this divisor is divisible by 4, and then this divisor is divisible by 2, or so on. Basically, we have to, as I said, distribute the powers of 2, the divisors of 2 into each divisor. But the problem is that we have to distribute them as such that we do not leave any slot empty. That is, every single position will have value distributed to it at some point. Let's, and for simplicity at the beginning, assume that P is equal to P to the power of some P. Then how do we compose? Obviously now, every one of these divisors, ignore the fact that it's +1, I might also delete that. As well delete that because it's useless. How do we compose D of a product of such divisors to get P to the power of T? Obviously, every one of these will have to be a power of T. So then we can just assume that we can take the logarithm of in base P, and then it would be equal to sum of logarithms. Each one of these is equal, is greater than 0, greater or equal to 1, and sum of these values is equal to some set value. We discussed this, it's called stars and bars. That is, that in such a case, we will have, I think, D minus 1 choose K minus 1. Is that correct? It is correct. Does everyone agree so far? I hope they do. And the issue is that when we consider that D is not just the power of P, but the power of multiple divisors, that we have to distribute all of the other powers into, and then forcing that every single power of every single prime power is at least represented at least one time in each divisor. Such a representation would be wrong because maybe a divisor is just 2 to the power of 3, and this is 3 to the power of 4. They don't have to all have every single prime base possible. So then we have to relax this, and then we're back in the issue that we might find that one of the divisors will be equal to 1. But for that, we can employ inclusion exclusion. So then, by the end, let's just factorize into numbers. let's define a solution for every possible size of k. That is, from the inclusion-exclusion principle, what we'd want to find out is the following. So let's say that one of these divisors is equal to 1. Then basically what we have is a solution with k minus 1. So then from our final set, we have to exclude every single solution of size k minus 1 and then choose which element was overrepresented. That is, if we know that we have t solutions with numbers, then we have to multiply t by k before we subtract it from the initially assumed solution. So if we are to find a distribution of d into divisors, but we are not sure if some of them would be equal to 1, then we subtract the count of solutions where we know that there are less than k minus 1 non-negative non-1 numbers, and then we choose which number was actually equal to 1 in our solution. And then we've composed, what we've done then is create a solution that we've clearly counted, but is wrong. Because we know that we inserted into a solution that is valid because it represents D as a product of divisors, but also has a number equal to 1. But then the issue is that the way that we count these values, that the way we would count the solutions with k minus 1 numbers would be flawed for the same reason. That is, it might be the case that we include here another solution where there is where there already exists an element equal to 1. So then if we consider 3 times 2 times 1 times 4 or whatever as a valid solution for k minus 1, then when we insert the new one to form an invalid solution, we will see that we actually double count either when we consider that 3 times 1 times 2 times 4 is the solution of length k minus 1, or when 3 times 2 times 1 times 4 is the solution with k minus 1. And then in both such cases, we may insert 1 on either side, and then we've basically double counted. So then in such a case, we also have to exclude the solutions with k minus 2 numbers. It turns out that by the end, the candidate count of solutions with k minus x numbers has to be multiplied by x minus 1 to the power of x times I think k choose x. And this is because consider a solution, a wrong solution, then the number of times it will be represented, I think, wait, am I wrong actually? No, I'm not. The number of times it will be represented in the solution upon multiplying with this coefficient. The number of times it will be represented as a solution with k numbers will be equal to as R flows. That is, R elements are equal to 1. It will be exactly one time. For K minus 1, it will be R choose 1, because we will choose which one of these elements we consider as the flow. And if we have K minus 2, then we can choose any of these two elements to be the actual flows. While there are still some flows in the original solution with K minus 2, we add two more to get to the final wrong solution. So basically we choose out of the final wrong solution which of these two flows we actually calculate. And for K minus 3, we have R choose 3, and so on. And because by the end, we have in the set of solutions with K minus of size K minus R, our actual wrong solution will be represented as an actual correct solution for size K minus R. But then we, in such a case, we still include and choose which ones to include, and that is all of them, all the flows back into the correct solution of size K minus R to get the wrong solution of size K. And then in such a case, if we add all the coefficients on the even indices and then subtract all of those on the odd indices, we will get basically the expansion of 1 minus 1 to the power of R. This expansion 1 minus 1 to the power of, this is obviously 0 if R is greater than 1, greater than 0. But the expansion of 1 minus 1 to the power of R is equal to 1 if R is equal to 0. That is, it will still be considered as a correct solution with, it will still be counted as a solution with K numbers, but it will never be able to be represented as a solution with K minus 1 numbers on which we add a flow. That is to say, so of I is going to be multiplied by the number of ways to distribute X exponents into K buckets, which is, I hope, X plus K plus X, sorry, minus 1 and K minus 1. Remind that we are now trying to calculate the number of solutions, regardless of flows or not, with length I, length equal to I. The reason for which we add I minus 1 is because, as I said in the original formula, we consider that we actually have a bit string of length X plus 1, for which the last bit is forcibly 1, and it delimitates the last bucket that we have. Okay. And we find the problem is related to stars and bars. Okay, so it starts when we want to represent D as a product of divisors, because we know D is the count of divisors of this value X, which would look like this. So if X is represented like this, its count of divisors, which is given to us, is represented like this, as a product of such divisors. I discussed that probably a way to calculate this, the count of such distributions into divisors of D as a means of dynamic programming will likely yield a very slow result, because we'd have to iterate quadratically on all the sets of subdivisors, basically. This is what might happen. Instead, let's assume a simpler case when D is equal to a power of T. Then, what do we know? That basically each of these divisors, although it's E1 plus 1, but ignore the fact that there's a plus 1 here, just assume that this is simply a divisor. Each one of the divisors that we split D into is power of P. So then we can just simplify this equation to the logarithm mod under base P of that. For this reason, why can we do this is because we don't really care that this corresponds to some P. This P could have been really anything, but what we care is that the number of times we multiply P or a power of P during this product would yield back P to the power of T. That is, we want to split into logarithms such that the sum of these logarithms is exactly T. And stars and bars told us how to split a greater sum into multiple smaller variables, such that these smaller variables have the ultimate sum as the original thing that we sought. That is, this is basically equivalent to S equals x1 plus x2 plus xk, such that xi respects some condition. For this case, it would be greater than 1, but we'll simplify that to 0. And yeah, that's it. We know that such a case is solvable. The number of such solutions is equal to S plus k minus 1 choose k minus 1. Is it here? D is the value that we get in the input. So they give us a D, which is the count of divisors of, so we have to count the number of values D that respect all of the following conditions, that they have exactly D divisors. So D is that value. And we said that since E will ultimately have to be represented as a product of prime numbers, and we can get the prime factorization of T, we can just assume that it exists, and E is equal to this product, because any divisor of T would have to have power of P1 to an exponent less than or equal to E1. So then we can choose this subdivisor of T to have P1 to 0, or P1 to 1, or P1 to the second, or so on up to P1 to E1. This could be the prime factor of the divisor under T. It could either have P1 to the power of 0, P1 to the power of 1, and so on. So then choosing in how many ways, choosing the exponent of P1 under T, choosing the exponent of P1 under T can yield back E1 plus 1 ways for this choosing. Here, it relates to this initial idea that D. So since D is a product of multiple divisors, we can instead, uh, if D were equal to P to the power of T, we would really care on how we can distribute the exponents to each of the divisors that will ultimately have to split D. We'll have to split D into. So then instead of thinking as D equals to P1 times P to the power of 2 times P to the power of 1 times P to the power of 5 and so on, we can say that D is equal to log base P under log. It looks like D equals 1 plus 2 plus 1 plus 5. So D is the, it's assume easier case for the input when D is equal to P to the power of T. That is, D is equal to a prime number raised to some power. That's it. So P is a prime number. P is an arbitrary. And in such a case, D into a product of divisors will it's not a prime D, but D that is a power of a prime. Because obviously, if D is equal to a prime number, then D has only two divisors. So then D would have to be either P times 1 times 1 and so on. This case is trivial, basically. If D is equal to P to the power of some T, then it gets difficult. It gets a bit more difficult. So then, instead of representing D as P to the power of 1 times P to the power of 2 times P to the power of 1 times P to the power of 5, we notice that P is basically redundant. We don't really care because only at the end we care that P to the power of this 1 plus 2 plus 1 plus 5 is equal to D. That is, 1 plus 2 plus 1 plus 5 is equal to log P of D. That is, as we've denoted, so then we have a value, and we want to split it into smaller values such that their sum is equal to that value. So then it's this, which is basically just bars and bars, well established. Is that fine so far? The idea is the following. So D is equal to P to the power of T. Why do we want this? Is because we've noticed that if we are to make a DP where we select every single element one by one, it will get difficult. But we notice that a case when D is equal to a power of T, that it doesn't really have to be this difficult to, because it's just a value that we can compute, a binomial coefficient. Now, in the case when D is equal to P1 to T1 times P1 to the T2 times so on, we can apply the exact same reasoning, only that we distribute all these powers of P1 to each divisor. That is, we first consider D prime equals P1 to T1, and we create a solution for these numbers that might look like A1 times A2 times so on. AK. These we know how to calculate because we've established its binomial coefficient in their factorization. Okay, so uh, normally I said we will ignore that and that it's just a binomial coefficient that we add at the end because consider then that, okay, let's go back to the initial. So A is equal to these values. It's equal to P1 to the E1 times P2 to the E2 times so on. And then, so then D is equal to this much. Notice how it doesn't really matter what values we choose for P1. That is, it could have been 3 to the power of 5 and we'd still have the same count of solutions for D, or well, 101, I'm not sure if it's, and so on. This, and the count of these would still not change. So we can put whatever we want here, and the count of these will still not change. So then the only thing that we really care about is that we do not double count. That is, if we are to count both this solution and this solution simultaneously, then it's bad. So what we only have to do is select a set of prime numbers, all less than p, and obviously this thing, that we will, with which we will fill these placeholder slots in the prime factorization of t. And also we impose that we will place them in increasing order, so that E1 plus 1 would correlate to the prime of the smallest prime power. Then E2 would correlate to the second smallest prime power. Because obviously, if we consider both the solutions, this solution and this solution, and this solution is basically equivalent to 11 to E2 times 17 to the E1, which technically is already calculated. Only that is the value. So then what is sufficient to do is count the number of ways to split D as a product of K divisors. Yeah, we have to split D as a product of K divisors. We try to calculate in how many ways we can choose these E1, E2, and so on. And at the end, we just multiply by in how many ways we can choose K prime powers, K prime bases out of all the prime powers that exist. Yeah, so should I go over the explanation of the inclusion-exclusion principle and why it's applicable here as well? Because I think we've gone over what I mean by distributing all the powers. So then this is the stars and bars factor that we have over here. And what it means is this inclusion-exclusion last lines, these are. Can I zoom out? Is it still visible if I zoom out this much? So the issue with distributing powers of 2 into D is that obviously when we have this, okay, so D1 equals X1 times X2 times, we have 2 to the power of 100. We should not expect that every single one of these divisors. So what we want is that every divisor is greater than one, because then it represents a time exponent that is greater than one. If this were equal to zero, then actually that prime power does not really exist in T. So we are wrong to assume that there are k prime numbers in the factorization. So every single divisor we split D into has to be equal, has to be greater than one, strictly greater than one. So then at least greater to two. But then if we have to split 2 to the power of 100 uh, and distribute all the entirety of 2 to the power of 100 to each of these divisors, it is wrong to assume that every one of them would have to be equal to 2. It would be easy to do so because if everyone would be divisible by 2, then they wouldn't give 10 minutes for you to explain it to them, I assume. And I just wait. No? Okay.
Xo'p, bolalar, Pakashto mana shu tushuntirgan joygacha tushunib olaylik, nima deyapti o'zi. Masalani hammamiz bilamiz-a? Hozirgi masala. Bilmaysizlar ham masala qanaqa bo'layotganini. Ha? Boshini o'qimayapsizlar-da sizlar. Aytyapti, masalan, ochib o'qib tursanglar ham bo'ladi-ku. Ha, G. Xo'sh, bilasiz. Nima ekan sharti? Xo'p, xata harfi prime. Ha, exactly kata prime distinct numbers va prime faktorizatsiyalari less than or equal to p. Birinchidan nima ish sodir bo'lishi kerak? Divizorlar soni aynan delta bo'lishi kerak. O'zbekchada NBC deymizmi? Natural bo'g'izlar soni. Bu narsa aynan delta bo'lishi kerak. Prime faktorizatsiyalar soni kata bo'lishi kerak. Kata demak bizda prime son bo'lishi kerak. Va hamma prime soni menda p dan kichikga teng bo'lishi kerak. P dan katta bo'lishi mumkin emas. Xo'p, buni qanday ishlasak bo'ladi deb so'rayapti. Ishlaganda chegaralarimiz nima? D 10 14 gacha. D bo'lishi mumkin bizda 10 14 gacha. Дальше 10 K 100 gacha, a P milliongacha. K 100 gacha, a P 10 6 gacha. Mana shu ishlaydi deyapti. Buni daychi hozir to'liq ishlashdan oldin D ni qaysidir propertilari uchun ko'rib chiqay. Aha. То есть bu shunaqa mana har bitta sonni men bunaqa yozibsizlar p1 ko'paygan p1 darajasida p1
So I assume this inclusion exclusion explanation was not covered. Or the rest of the implementation, whatever. So this is the explanation of why we should apply inclusion exclusion principle. And this is basically a template for every single time that inclusion exclusion principle appears in any task. So what we do with the stars and bars is that we distribute powers of 2, or 3, or of 5 that compose D to each of the slots that we are to, each of the divisor slots that compose D. So in this example, 2 to 100, we split it as 2 to the power of 17 times 2 to the power of 15 times so on 2 to the power of 15. And then 3 to the power of 12, we split it like whatever. 5 to the power of 6, we split it like whatever. And then we multiply column by column to get the final solution. So this is what we do with the stars and bars. The issue is if after we do stars and bars, the astronomically low chance that will still occur happens that one of these values will have 0 all throughout the column. That is, it will be to the power of 0 times to the power of 3 times 3 to the power of 0 times 5 to the power of 0, that is 1. If xi equals 1, then the ei plus 1 that it represents would make ei equal to 0. So then t would be equal to pi to the power of 0. So then t doesn't actually have k distinct divisors. So let's then call f of d of k the count of divisions that we count with the stars and bars formula of d into k divisors, which is basically the product of all the stars and bars, but where we might vary k. And let's take a wrong solution that we consider, where we know that some indexes are equal to 1, and there are a total of 80 such indexes. Yeah, then obviously we count it more times than we should in fd of k. That is, we count it exactly 1 time. We won't count it more than 2 times because we don't. This is a perfect bijection. But then consider the count of solutions of splitting d into k minus 1 numbers. And what we can do now is construct a bad solution starting from this solution that might be represented in fd of k. And we will do this by inserting a 1 randomly somewhere. So then we consider a1, a2, ai, 1, ai plus 1 up to ak minus 1. This has k numbers and is a wrong solution. But then we notice that we might construct multiple times the same wrong solution. That is, if let's take the wrong solution 1 times 1 times 1 times 1, for example. And this can be constructed by inserting 1 into the wrong solution of 1 times 1 times 1 for k equals k minus 1. To this, or if the placeholder is instead someplace else, or if the placeholder is someplace else, and so on. So for each way to choose the actual wrong index in the actual wrong solution that we represent here, what happens is that we overcount this wrong solution by creating these bad solutions from fd of k minus 1 a total number of t times. But although this is a bit discouraging because we overcount something a lot of times, and maybe we just wanted to subtract it one time. We just wanted to subtract the wrong solution one time and be done with it. We consider what would happen if we try to do the same thing for fd of k minus 2, where we then insert at random in the solution two values of 1 somewhere. Then, in such a case, for this wrong solution, we overrepresent it in this factor by t choose 2 times. That is, we choose which of these two flaws we actually insert here, and then basically the solution that we count here uniquely will be those two flaws that we fixed, erased from the initial wrong solution. So then by the end, if we do this for every lesser set of elements, and after that we insert x elements equal to 1, we get that in f of e k minus 0, we overcount this specific solution, t choose 0 times in f d of k minus 1, where we generate a solution of length k minus 1, and then we insert forcefully a 1 in every single position of that solution. We overcount this value, t choose 1 times. Then in k minus 2, and then in a solution of length k minus 2, where we later insert two values of 1, we overcount it by t choose 2 times. In a solution where we select a set of k minus t numbers to split d into, and then later we insert exactly t values of 1, we calculate it t choose t times. That is, this is the only time that we see an actual correct solution, but it is for the wrong size. And after we adjust it for the right size, it has exactly all the flaws that our initial wrong solution has. We then think to add all the elements on the even indices and subtract all of those on the odd indices. When we do this, we notice that if t were greater than 1, that we actually expressed the expansion of 1 minus 1 to the power of t, which is 0 times. So then if we add all the positions, all the values on the even positions, and subtract all of those on the wrong positions, by the end, we will not have counted any wrong solution at all. But all the correct solutions are represented at least one time in the original f of d of k. And they will never be represented as an extension of a smaller solution after which we insert the 1, obviously because the solution is correct. So by the end, after adding all of these elements on the prime, on the even indices and subtract all of those on the odd indices, we will have a number of all the correct solutions. So this is essentially what we do here. We calculate the stars and bars solution for every way of choosing the length. So for length 1, we might notice that this value will be equal to 1. That is clearly because d split into 1 divisor can only be equal to d, and so on. We calculate every single way of splitting d, that is these prime exponents, into multiple boxes of every single possible length. And then we add and subtract, something is missing, all the wrong solutions. And by the end, we should have a correct solution. Is that clear? It's still surprising. Uh, no, god damn it. Okay. So, should I continue with the next task? Is everything clear for this task? Yes, I would say. Unfortunately, the time is now short, so I'll just cover the fuel create, the fictional problem branch. That is the one where we have to calculate a set of intervals R such that GCD of L and EL to ER is greater than max of BL to BR. So what I said we have to do here, I think I can finish this one. The implementation is that we have to have a stack that this problem can be solved by two pointers, and then two pointers implies a queue-like structure on which we need to have GCD and max. So that we will split the queue into two stacks. So let's start by doing that. Let's construct a stack that can calculate all the GCDs and all the maximums. Okay, so we have vector T stack and vector T hammer. This hammer. If we should end by now, we will end now. Okay. Yeah, so then goodbye. Yeah, I'll try to finish up the codes for this task and task triangle. And I'll send it to you and maybe we'll discuss over this one. Okay.
In front of the ekran.
In front of the what?
In front of the ekran.
Monitor. That's a monitor. Ekran is Russian.
I know.
It's not Russian. It's Russian. Russian. То есть men buni yaxshilabda quick qarab chiqishim kerak. Oxirini buzib tashladi. Men o'zim hali tushunganim yo'q. Qachon tushunsam, keyin tushuntirib beraman.
Qaysi masala?
Hozirgi masala. Tushuntirasizsiz?
Homeworkdan emasmi?
Ha?
Homeworkdan.
2 kun oldingi homework.
Ha, masala.
Divizor. G.
Почти ishtadik bizlar ham shuni.
100 ga?
Почти.
Ama tushuntiringmi bolalarga? Men hali tushunib yetganim yo'q.
P emasmi shunda? Просто C. Prime'larni C bilan darajalarni qanaqasini half. What's the way? Oddiydi.
Oddiy.
Let me
Tushunmas shekilli.